Hello, everybody. Hope your week is going all right. I'm this week's primary presenter. The secondary presenter for today is Samuel Mendoza, who's been great in doing his part. Since I'll be emceeing the presentation today, I think I'm going to take just a few seconds to introduce myself. This is me. Don't mean to brag over my 5K run, but I seriously couldn't find any better picture than this. I realized just yesterday that I actually don't have any decent pictures of myself since like quarantine started, except the few you got this bathroom mirror selfies, but nobody needs to see that. So let's move on. One of the two topics this week is new technology relationships. I chose this particular topic because I like to stay up to date with technological innovations, and with each breakthrough, it looks like we'll never be interacting with technology the same anymore. For instance, take the case of the phone. Did Graham Bell have the same relationship that we have with phones? Of course not. So, hopefully, that gave you a tiny glimpse into what our topic could be. So, without further ado, let me get to one of the biggest but definitely worthwhile reading assignments of this week: coactive design, designing support for interdependence in joint activity. This is kind of like a theoretical paper, but don't worry, I'll explain everything you need to know and I'll try to keep the presentation as short as possible. I'm gonna break this paper down into three basic questions: why, what, and how. And we can just start with the why. So, why is this topic important? Well, as you can see on the slide, with increasing automation, the intelligence of robotic systems and their task execution capacities are increasing astronomically. Robots are no longer simple computational systems that can just do as programmed. Machine learning and AI advances, such as deep learning, allow robots to learn, and hence they can kind of take a role alongside humans in execution of most tasks, actually. So they can cooperate as teammates. And in fact, plans to roll out automated assistants are already underway. So all of these points highlight the importance of studying this topic. Now, going by the same line of questioning, you could probably ask, why do we need to focus on this particular paper? What's so unique about it? Well, for starters, this is our assignment, so take it up with Dr. Cho. And also, it's a really interesting paper. So, human robot teaming, which essentially encompasses the topic of this paper, is considered by many to be highly academic due to its abstract and theoretical research output. Models of teamwork that have been developed by prior research mostly tend to be in terms of these high level behaviors, which are definitely valuable, but don't always get embraced by systems engineers because they're not very specific. Hence, this paper kind of, works on these particular issues, and it tries to translate these high-level concepts such as teamwork and collaboration into implementations in terms of control algorithms, interface elements, and behaviors. Now let's kind of go to the what questions. To understand what this topic is about, we just need to take a closer look at the title. Let's start with this. What does the term coactive mean? Coactive is when humans and machines are jointly engaged in an activity. And they aren't just engaged, they also exert influences on each other, reciprocal and mutually constraining effects conditioned by coordination. This sets us up nicely to dig into the next term, joint activity. A joint activity describes the nature of the activity, and as the name suggests, it requires the combined efforts of two or more contributors. So we understand what the task is, but what does designing support for this task necessarily mean? As you probably guessed by now, it just means designing, keeping the characteristics of coactiveness and joint activity in mind. So this means the design should reflect and encourage the various relationships between the contributors. So that brings us to one of the key terms of this paper. interdependence. Interdependence is defined as the complementary relationship that two or more parties rely on to manage dependencies in joint activities. While this seems like just another definition, the authors in the paper go into great detail about the evolution of how they came up with their own definition of interdependence, which is frankly quite interesting. So I'd suggest you give it a look. Also, since interdependence is like an integral part of this paper, let's delve a tad bit deeper into this term. Many misunderstandings in science actually come from assigning different meanings to terms. So the paper rightly recognizes this fact and talks about the important difference between interdependence and dependence, at least in the context of this paper. So these two terms have been used interchangeably in previous literature. But after reviewing tons of works from organizational theory, social psychology, AI, and many other multidisciplinary fields, the authors concluded that dependence exists when an entity lacks a required capacity to competently perform an activity in a given context. Whereas interdependence, to add on to the previous definition, describes the set of complementary relationships that two or more parties rely on to manage required and opportunistic dependencies in joint activity. Now you can see that here, interestingly, the authors introduced the concept of soft and hard dependencies. As you can see from the picture, this is taken from the paper, preventing train crashes is a hard or required dependency. But getting yourself and your kid to walk on the rail tracks, balance on it, achievement unlocked. It is a bonus gain for sure. But even without it, you can still lead your normal lives, right? So, but being able to do so gives them enjoyment. So it's a soft benefit. So you could consider interdependency to be dependency of two entities on each other, so a mutual dependency with not just hard benefits, but also the soft benefits. So we've discussed some important and fundamental concepts. I think we're ready to ask the how questions. How can interdependence be applied in the real world is the question. The authors of this paper based their application model on Fong et al.'s collaborative control system model from their paper in 2001. The role of the humans in this model is to provide assistance to a robot that is trying to navigate. So basically, the human supplements the robot's limited perceptual and cognitive capacity by quote unquote closing the loop. To kind of use the same examples that were brought up in the paper, an example of a perception question in this context would be, are these rocks? An example of a cognitive question would be something like, can I drive through these rocks? Some interesting things with this model is that Fang et al. Break down the robot to multiple levels of perception cognition, showing that a human could choose to close the loop at different levels of perception or cognition within the robot. So I think that sets us firmly to move on to the proposed model which the authors of this paper have proposed. The authors suggest a coactive system model which hinges on three important requirements: observability, predictability, and directability. So that's OPD. So observability is ensuring that the system status, knowledge, and environment conditions are available for other contributors. And since interdependence is like a complementary relationship, it includes observing and interpreting signals from teammates. Predictability means the actions should be predictable enough that others can reasonably rely on them when considering what actions they themselves must take. Once again, since interdependence is a complementary relationship, it is important to have mutual predictability. Directability means one's ability to kind of direct the behavior of others and complementarily be directed by others. So directability could include explicit commands for task allocation and role assignment, or maybe even subtler influences like providing guidance or suggestions, or even just giving warnings. So, an important point to note about the OPD requirement scheme is that the goal of a designer shouldn't be to maximize or minimize OPD, but to attain sufficient OPD to support the necessary interdependent relationships. As a quick example, increasing observability to the maximum could confuse a user, or maybe decreasing it and keeping it to the bare minimum could maybe um, equally confuse the user as he or she cannot observe what's going on within the system. So that's an example of why it is necessary to be sufficient, not maximize or minimize. So another thing we can see from the model here is that sensing from both partners relates to observability, planning and intentions pertain to predictability, prerogatives to act, decide, directability. In this slide, let's try to understand the differences between Fong et al.'s model and this proposed model. So it actually doesn't contrast with they actually don't contrast with each other, but rather the proposed model extends Fong et al.'s model. The collaborative control system model focuses mainly on a human supplementing a robot's deficiencies, but the coactive system model introduces human as a full actor in the system alongside the robot instead of just as a controller. Secondly, the proposed model also adds more detail to the machine's internal processes. Perception and cognition were pretty much the only stages in Fong's models which could actually break down to many different things. This model, the proposed model, now adds more layers, giving it specificity by giving it different stages. Finally, the model also moves from taking a task and breaking it down to actually centering around interdependence and splitting the team into functional components using the interface layer. Another quick note is that the internal models provided in the proposed system are not final, they're just examples. So the designers can actually replace them with the levels of abstraction or specificity that they need. Another important how question is finding out how we can implement this framework. For this purpose, the writers of the paper have given an intense looking flowchart that is very comprehensive. Broadly, the process can actually be broken down into three sections: identification, selection and implementation, evaluation. So the identification stage is an extension of the usual task analysis by taking the team member capabilities and knowledge also into consideration. So the second stage, selection and implementation phase, takes these proposed relationships from the identification process and determines the best mechanism that can be employed for successful collaboration amidst them. And finally, the evaluation of change is like a reiterative design step. It's critical because the choice of mechanism can influence interdependent relationships, which is not ideal. So we might need to go with a different mechanism. So evaluation is when that comes into play. Out of these three phases, as you can see from the flowchart, the identification phase is kind of the longest. So let's just actually spend a couple more minutes on how the identification process goes. These images have been taken from the paper, and they do a great job in explaining how each of them need to be used. So just to quickly run you through them once again, in the image on the left, you can see that the left half of the table is traditional task analysis, so that's the usual. The right half of the table, however, is the team member roles sheet. So this sheet is supposed to be filled with different shades of color. As you can see from the top image on the right, different colors mean different levels of activity performance. On the performer side, um, green could be all clear, task can be done, so there is no issues. Yellow is like a little bit lower in reliability. Orange is a hard requirement, which means it absolutely needs help. and red is simply a no-go. This means it can't be done. So the performer side and the supporting team member side could be human or robot, alternatively. So there could be multiple alternatives. You should kind of find an example in the table on the bottom right. So that's an example that they gave. As we discussed earlier, observability in sensory inputs, informing interpretation, which is bolstered by humans' knowledge, which then could be used to direct the robot, giving way to directability. So essentially, observability takes the sensory inputs. I mean that is observability is the sensory inputs informing interpretation, and then humans' knowledge bolsters it or strengthens this, and then that could be used to give directions to the robot, which is directability. That's what the arrows signify in that image. For the final slide of this paper, I'm going to quickly go through how this framework was utilized by the authors in the DARPA Robotics Challenge in the virtual round. So the robot in the challenge was supposed to help with a natural disaster-based rescue operation. The task analysis is not shown on the table. We are looking at how the team member roles could be interpreted. As an example, let's consider the first row. Sensing the hose is the task. R and H in the team member role alternatives section indicate robot and human, respectively. So there are two alternatives in this case, robot as the performer, which is the first case, or human as the performer, which is the second case. In either of the cases, only the performer of the task can sense, and hence the other one can't help with the task. Therefore, as you can see on the interpretation, it says is that either can sense it independently. And this is evident from the two alternatives also. So this approach was taken for each capacity. Feel free to go through the table, and I would suggest that you work it out for each of these capacities because that's how I got familiar with how to use the framework. Um, yeah, if you want to do a little bit of an exercise, that definitely ideal. Alrighty, so we've covered a lot of ground very quickly. If you haven't gone through the paper, you won't even realize it. But now we just have the smaller paper remaining. We're almost at the end. So off we go to the next paper. Today's second paper is titled Awareness, Training, and Trust in Interaction with Adaptive Spam Filters. So the paper definitely provides interesting insights into how trust can be studied in systems such as these, which are used by almost everybody knowingly or unknowingly. If you have no clue what I'm talking about, hang on for a few slides and you should be all caught up. So to give you all a change of pace, let me try to sum up what the paper is trying to achieve with a single GIF. GIF? GIF? I don't know. Never done this before, you say? Do not fear, Shrikar is here. Spam emails are generally the unsolicited marketing and advertising emails that we often get. If not for spam filters, our inboxes would pretty much be flooded with them. Since no spam filter is perfect, we occasionally do see those junk emails come through, but these algorithms have been getting better and better over time. So to put it in terms of this little animation, the diligent robot that you see is the spam filter. Its home is our email. We trust it to weed out those junk or spam mail and give us only the important mails. There we have it. The paper is about awareness, which is knowing that these filters exist. The paper is about training, which means different filters are built different. So how does their training affect us? And the paper is about trust. So trusting them to safely handle our emails when interacting with adaptive spam filters. So adaptive simply implies that they learn. So if they missed a spam email and you mark that email as spam when you see it, then your spam filter will remember it for next time. So this is essentially what the paper is about. All right, now let's get down to the text. So the main aim of the paper is to investigate user attitudes and trust towards adaptive or trainable as well as non-trainable filters. Let's quickly look at some background information before we discuss how the experiment was carried out. So here are the important points that you need to know in order to make sense of the results. Users tend to trust a system based on the competence of the system. Although a user may trust a system, they will not rely on it if the perceived risks outweigh the benefits or if they can outperform the system. So if a user can outperform the system by himself or herself, then they will not want to rely on it. And then if a user perceives higher risk than benefits, then also that makes sense that they would not want to rely on the system. User awareness is another very important point. Users must know the existence of the system. It is kind of obvious. If you do not know that it exists, then, well, yeah. So, apart from its sheer existence, they also must know that the system can give feedback or that the system can be trained. So they have to know that the system can be given feedback, like you can give the system feedback, or that the system can be trained, without which they would not make that act, do that conscious effort to train the system, which is, a waste. So for the trainable filter to learn what is spam and what isn't, it requires user feedback because not all filters are 100% right. So all of them, in fact, do have some margin of error. And in the beginning, the margin of error is often higher. And as you train it, it keeps getting lower until it almost reaches 100%, but it never will mathematically. But yeah. So training improves performance, which is expected to increase trust. But training is often slow and users' trust declines upon noticing errors faster than it ascends upon correct classification. That's just how our mind works. We register negative emotions better than positive. So that's that. This experiment was kind of conducted on 43 different participants, and they were split into three groups. 12 of them were assigned to work with an adaptive filter, 19 of them with a non-adaptive filter, and 12 of them with both. So an adaptive filter is the one that can train, that can learn. A non-adaptive filter works on a set of rules. It has no margin of learning. So it is either yes or no, so it just does that. An adaptive one learns based on your preferences and your corrections and stuff like that. So the experiment involved user observation, interview, and survey techniques. To measure user attitudes, participants were surveyed and questionnaires that covered questions concerning perceived filter usefulness, perceived ease of use, attitude towards spam filter, and dependability of the filter were kind of given out. And then participants that essentially allowed the system its autonomy were more positive on usefulness, ease of use, and overall attitude towards the filter. Like they were more positive in their overall attitude towards the filter. I'm talking about the participants who allowed the system to function on its own. Critical errors or false positives hinder trust in the system. So this makes sense. So when I say false positive, I'm kind of buying into the idea of signal detection. And false positive means that it is not spam, but it got tagged as spam, which is deadly because like that could have been a very important email, right? So that is a critical error. The differences in the algorithm being trainable versus untrainable were not significant. So they had different groups try different kinds of algorithms. Some were trainable, some were untrainable. Turns out doesn't matter that much. Attitude scores for those that trained their filter were significantly higher than those that did not. So people who consciously trained their filter, they had better attitude, like better attitude scores towards the filter than those who did not. That's what the line says. And the sheer presence of active filters did not guarantee correct usage. This, once again, it's easy to assume that people will not correctly use it just by keeping a piece of technology there. They'd have to be like trained, or they'd have to see how to use it. So UI guidelines have to be strictly followed. When users assumed the spam button was the delete button, they inadvertently trained the filter to remove non-spam email. So this happened in the paper. Users kind of assumed that the spam button was the delete button. So every time they selected a bunch of emails and then clicked on what they thought was delete, they were actually marking them as spam. So those emails could have been from their bosses and they were marking them as spam. So their next boss email would go straight to spam if they trained it long enough. Yeah, so that's deadly. So UI guidelines should follow strict rules. So users should be allowed to train exceptions or special cases, as it was seen that rather than trust in the system, trust in the training process plays an important role. So when users believe that the training process is sound, when they really trust the training process, that makes a major role in making sure that their attitude towards the filter is more positive than simple trust in the system. So users should be allowed to train exceptions or special cases, and they have to be able to give feedback. So these exceptions or special cases are nothing but feedback to the filter. So by allowing them to do this, you're allowing them to invest into the algorithm, the filter itself, because they're actively trying to guide it. So this means they would trust the training process better, and that's why this is like a recommendation. And then awareness seems to be a key theme, and especially when designing systems that are in the background, it is important to ensure its presence is still felt by the users in order to boost user attitude. So a spam filter is not something that has an icon, or it's not something that you can reach or tap or click. A spam filter does its thing on its own. It's like a background entity. So designers have to kind of come up with ways to make sure that this is being understood by the users, in order to deliver its presence, in order to make them aware that it's present. Because clearly the study showed that when people are more aware, their attitudes are better. So that makes sense. And then user has to feel confident about the fruitfulness of the training. This can be achieved by educating users on how it works, or in similar ways to build credibility. So again, this kind of goes on to the previous point that we were talking about, the fruitfulness of training. They have to feel confident about the effectiveness of the training. So for that, you need to kind of educate them on how training is beneficial, and this is a good way. This can be done through building credibility. So you can say that this algorithm needs these many iterations of, like educating users. It depends on what kind of users they are. So if they're just normal users, then you would just educate them in terms of the awareness, and then build credibility based on that. So once again, we talk about edge cases in the conclusion, or exceptions, we can call them either, so that the users can also avoid false positives. So they have to make sure they can give feedback to the filter so that false positives can be avoided at all costs. All right, so it's been a great ride, and hopefully you learned something of interest. I've had great fun making this presentation. All that being said, here are this week's discussion questions. I'm sure you've been looking forward to this. And thanks a lot for your time, and have a great week.